welcome everyone to my talk. My name is Gergő Huszty, and today I would like to talk about public clouds, that's some Kubernetes things, and open source, which all powers that. Okay, so I consider this content as an advanced topic, simply because I assume you understand how Kubernetes is built up in general regarding its master components. Okay, so we heard a lot of good talks about public cloud concepts today, so we will go a bit deeper today. We also heard how to scale a single cluster from network point of view in the previous talk from Richie, so we will not cover on that, we will cover other topics. Okay. Okay, so my name is Gergő Huszty. I like to work for companies with blue logos. Last year, I joined IBM to work on IBM Kubernetes Services. Yeah, and let's jump right into it. Okay, so this content is not about the latest and greatest offerings from IBM. The content often shows existing and mature products and solutions, simply because it is easier to understand. And here and there I created some simplifications in order to fit to the time slot. Okay. So if you know IBM only for the great laptops back in the days, you have to know that IBM is also a public cloud provider and manages many data centers around the globe. And that's what we will check in details today. Okay, as far as open source, you might expect some components in the public clouds. Naturally, an operating system like Linux, Kubernetes, which is everywhere today, even some modern programming languages with open ecosystems are naturally there. We will touch on them, but we will see some other interesting cases as well. Okay, the most important thing, how to scale clusters. I mean, how to scale a managed Kubernetes service where there are potentially an infinite amount of clusters deployed in a single public cloud. Usually, when you create your own Kubernetes cluster, like with K3s or with other sandboxing tools or on your own data center, you probably end up having some master pods. Let's call your cluster cube X. So you have a bunch of pods running right in your cluster, which they are controlling as well. So the master components are really only a few pods. Now, in order to reach this control plane, it is usually exposed by a Kubernetes service, which is like a logical construct implemented via networking tools on Linux. So then you have a bunch of worker nodes, whatever kind of worker nodes, being virtual or physical, and at least the node agent on the worker nodes are contacting the master using this service, which exposes them. The same service or other service objects can be used to expose the master services externally. It is not shown here, but we will see that as well. Okay, so this is where we start. Now, how to scale it? As I said, the master components are just a bunch of pods. It is usually running in your cluster, but it is not a mandatory thing. So as long as there is network connectivity between your master and your worker nodes, the master can run anywhere. So let's say you have your customer account in the public cloud, where only your worker machines are deployed, and then you have your master pods running totally elsewhere. Now, of course, this is in a single compute region, and then let's say the place where your master components are running is yet another Kubernetes cluster, which is not in your account. It is behind the scenes, and this is where IBM manages your clusters. So then, after deploying masters on another cluster dedicated for this purpose, you can actually scale it up and use similar deployments in case of other customer accounts. So the customer account is safe and isolated with all of its workers, and the tugboat is hosting all the masters and exposes the services exclusively to that customer account. Now, usually we can say that the customer account is isolated, and it means that there is no direct IP routing between the customer account and the service account where the tugboat is running, which means we have to put a magic box in front of the tugboat, which is called the service endpoint, which is exposing special IP addresses, which are routable from any customer account. And of course, there is a lot of firewalling and so on, ensuring only your customer account is able to reach out to the respective master components. Okay, since it is a managed solution, we have some management service implemented and deployed on the tugboat, which is managing mainly the life cycle of your Kubernetes clusters. And now we are good until a few thousand of Kubernetes services, which is kind of the limit of such a tugboat. But no problem, we can have any amount of them, basically reaching a virtually infinite scalability. Okay, now we have another management issue. We have multiple tugboats in the same region with potentially similar customers deploying the clusters on multiple tugboats. So we have to also coordinate all of this one. And so we introduce another level of Kubernetes cluster, which is called a carrier, which mainly manages the tugboats and not the life cycle of the end user clusters, but the services deployed on the end user cluster as well. So we have a different kind of management services deployed on the carrier. Okay, so as you can see, the secret to host multiple Kubernetes clusters is only Kubernetes itself. Note that there is no such embedded virtualization or running the worker nodes in containers and so on. These compute workloads are deployed all on the same flat IaaS, only in different accounts. So yeah, as we only decouple the masters from the workers, we reach the desired managed solution, basically. Okay, Kubernetes in Kubernetes. Okay, what are the management services? There is really nothing special there. For the tugboats, which are managing the life cycle, I mean the deployment, the upgrade, and the decommissioning of the end user clusters, is mainly deployed with Ansible or managed with Ansible. We have tons of Ansible playbooks which are coordinating all of the life cycles. Of course, we glue it with a bit of Go code. Oh yeah, I haven't mentioned that if you check the tugboat master is running similarly elsewhere to the customer cluster, which means the carrier is able to directly manage the tugboats similarly how the tugboat manages the end user clusters. Yeah. Now the carrier also has the task to manage the services and coordinate all region-wide the services on top of the Kubernetes, the end user clusters. It is usually implemented in a lot of, or in a bunch of Go microservices operating on top of a shared etcd cluster, which is basically having the region-wide persistence for all the service states. Yeah, so that's how we manage Kubernetes clusters, basically. Okay, now going to a bit deeper, there are some tricks to have the proper worker-master communication. If you are familiar with the Kubernetes architecture, you know that there is a two-way communication between the workers and the masters. First of all, or in the most often cases, the worker node and the node agents, which is the kubelet, communicates towards the API server to fetch and sync everything which it has to deploy. So that's the most common direction. So the service endpoint exposes the master in a well-known in a set of well-known IP addresses behind DNS names, which means it is directly routable from your workload. But we don't rely on kubelet logic to have an HA connection towards the multiple IP addresses. So we introduced a man in the middle, which is an HA proxy, which is an open source component, and it does a great job on keeping a high available connection towards the multiple service endpoint IP addresses. Now, in order to really have it locally everywhere, we deployed this HA proxy on all the worker nodes, and basically the worker node has to only contact a local IP address, and HA proxy does the magic to connect to the real API server. Now, in more rare cases, the API server wants to connect back to the workers, which is in case of you want to fetch logs or execute commands on already running pods. So, as your customer account is isolated and the API server is not able to reach directly into your private subnets, then we have to inverse this dependency, and so we create a dedicated OpenVPN channel. When the server runs on the tugboat, it is dedicated to your customer cluster. It is exposed similarly to the API server behind the service endpoint, which means if there is a VPN client with the same OpenVPN component on the cluster, it is able to establish the VPN connection towards the service, which means if the API server is configured properly, it is able to use that secure connection to connect back towards your worker nodes. Now we use a single VPN client to reach out to all the worker nodes, which may have some obvious drawbacks. It might be swapped in the future to something more reliable, but it is so far so good. Okay, so this was about how we connect workers and masters. Let's see how we expose applications in a very simple infrastructure as a service. As I said, this is not the most advanced offering from IBM. This is the infrastructure type called Classic, which is providing very interesting low-level resources, by the way. Okay, so we have a region, we have a bunch of zones, computing zones there, and in this IaaS, you are able to purchase either private or public virtual LANs directly. So it will be assigned to your customer account. Naturally, the public VLANs are actually exposed towards the public network, which is the internet, but also the private VLANs are connected together. Yeah, so you are able to do cross-zone traffic without reaching out to the public network. On the bottom right, you can see cloud services, which, for example, is your Kubernetes service, your master components, which we just described in the previous slides. The cloud services are reachable also on private and public. That's how you can reach out to your API server using kubectl over the internet. Okay, after having proper connectivity in place, you can deploy any kind of compute resources to these compute zones, whether virtual machines or bare metal instances. So this is a very simple infrastructure as a service. It provides raw, understandable, low-level cloud resources, and usually the cloud services on top of this. These are really just regular users of this IaaS. Those are operating on top of the same APIs as the user would use, which means the user is able to inspect anything which is deployed on his behalf after, for example, he purchases a Kubernetes cluster. Okay, so how do we expose our favorite application in this environment? On this picture, you can see a single zone deployment of a Kubernetes cluster. You have your application pod. Of course, you can have multiple of them using deployments or daemon sets. And yeah, you usually expose applications on public clouds using by creating a service, a Kubernetes service with the type load balancer, which is triggering a special hook in your Kubernetes master. This special hook is implemented and invoked in a vendor-specific way. So every cloud provider is able to create whatever he wants, reacting to this service inquiry, which is to create a load balancer. So in this kind of infrastructure as a service, the solution is to directly deploy the load balancer actually as pods into your cluster. So there will be two kind of special pods deployed into your cluster to have HA. And there is an interesting component inside, which is an open source component. It is called keepalive. If you are not familiar with that, it is a small project which is an HA load balancer control plane. Basically, it talks a bunch of interesting protocols. For example, it is able to coordinate reliably to have with its twins. So it will allocate the resources only to one of them at a time, and it is able to fail over. Now, keepalive is not meant originally to run on Kubernetes or in IBM cloud and in any clouds at all. So it is just a small C project which we have to coordinate. So it is a common pattern to have an open source component and then a bunch of glue code right next to it. So there is a supervision process implemented in Go in the same pod, which configures the keepalive. It manages the lifecycle of the process, scrape logs, and so on. Yeah. So basically, the Go code understands what the environment is running in. For example, it fetches the IP address it wants to allocate, and after selecting the master and the backup, the master will announce the virtual IP, which will be reachable from the internet. It is basically announcing with the virtual IP towards the site router with regular ARP messages. So after that, when a user comes and connects to that virtual IP address, it will be directly routed to the compute instance where the master load balancer pod is running. And then the other task of keepalive is to set up a set of IPVS routes directly into the host kernel, which will direct the traffic properly to the application pod running anywhere in the cluster. Yeah, these rules are following wherever the application pod is rescheduled or scaled. You can select round-robin methods and so on. And the most interesting part is that it is able to preserve the source IP using this IPVS technology, which means the application pod seemingly will be contacted directly from the user. And when it responds back without any magic, the traffic will go directly through the public internet to the user without hooking the load balancer compute instance again. And of course, the site routers are prepared for such an extraordinary traffic. It is called direct server return. And yeah, next topic, how to manage all of this. I mean, how to manage multiple thousands of Kubernetes clusters in a controlled way. We saw how the masters are controlled and how the lifecycle of the clusters are controlled. Now we are talking about our control plane, which is still a lot of Kubernetes clusters worldwide, at least. So there was no such a great candidate to coordinate all of this. And so IBM invented its own tool chain. It is called Resi, and it is open source, so you can use it for your own purposes as well. Yeah, this is a resource management platform, which means it is not able to coordinate cluster lifecycle. I mean, creating clusters. It is able to run resources and update resources on existing clusters. It is data-driven, it has nice statistics and so on. And actually, including our end-user customer clusters, it is all in the RASi inventory, but we are only managing with the control plane of the IKS service. Yeah, so today altogether it is more than 40K clusters in the production RASi environment. Unfortunately, I'm not able to show you the dashboard. I would really want to, but yeah, there we are. I think that was all.